Now we are discussing about operational amplifier based Wein Bridge Oscillator. You might have already studied about oscillators in your previous semester. We generate an output by using the oscillator. We do not give any input, particularly any AC input for the oscillator. Here you can observe, but we generally give the DC supply, but we are not giving any particular input here. The oscillations are being generated. Initially, the oscillations are starting like this, and after a certain amount of time, stable oscillations will be obtained. Here, in order to generate these oscillations, we expect initially the A beta should be greater than or equal to 1, and here the A beta should be equal to 1. Now we are discussing about a audio range frequency oscillator. This oscillator is, we can use this oscillator in the range of 1 Hz to 1 MHz, but it is very much suitable in the audio frequency range from 20 Hz to 20 kHz. Why this oscillator became that much popular? Because of its simple construction. You see, we are only using one Wheatstone bridge along with our operational amplifier, and its stability at the resonance frequency. The output we are getting at the resonance frequency is a very stable output with very low distortion. Because of these two reasons, the Wein Bridge Oscillator became very much famous in the range of the audio frequencies. If you want to use radio frequencies, then definitely you have to take some LC circuit. Because I discussed about the audio frequencies, I am going with the RC circuit. Here you observe only resistor and capacitors are there. There is no inductor. So this is an RC circuit. This bridge is called as Wheatstone bridge. In this bridge we have 4 arms. In the 2 arms we have resistor and capacitor connected in series and parallel. In another 2 arms we have 2 resistors. These 2 arms decide the frequency of the oscillator output. Example, if you want to design 1 kHz frequency or 2 kHz frequency or 3 kHz frequency, then the frequency can be designed by using these 2 arms. The output voltage amplitude can be decided by using these 2 resistors. So these 2 resistors decide the output voltage amplitude. Now we are taking these 2 arms initially, a resistor and a capacitor in series and a resistor and a capacitor in parallel. Example, if we are giving an input at very low frequencies, you may ask question, sir, you are saying there is no input to the oscillator but still you are writing an input. Yes, you are absolutely correct. We are taking this output as input. The operational amplifier output itself we are connecting in feedback and we are saying that is the input. We are not giving specially any input, but this output itself will act as an input. Now we are assuming we are giving example to this. This is acting like a high pass filter and this is acting like a low pass filter. We will try to understand this circuit. The capacitive reactance Xc is equal to 1 by 2 pi Fc. At very low frequencies, this Xc value is very much high. So at very low frequencies, this capacitor will be open circuited. It will not allow the low frequency signals. That's why we are calling this as a high pass filter. And at high frequencies, this capacitor will be shorted, very good. But this capacitor will also be shorted and this capacitor grounds the entire signal. That's why we do not even get the high frequency signal also as the output. So this is acting like a low pass filter and this is acting like a high pass filter. This C1 capacitor, when we are giving the low frequency signal, it is being open circuited, and at the high frequency signal this C2 is becoming short circuited and it is shorting signal. We are not getting signal at low frequencies because the C1 capacitor is open circuited, and we are not getting any output at the high frequencies because the capacitor C2 is short circuited. Then what we have to do with this Wein Bridge oscillator? You are saying it is not giving any output at the low frequencies and high frequencies. Then what is the use with this? Now we are trying to understand, is there any frequency which is not low and which is not high? That frequency we are calling as a resonant frequency. At this frequency, the capacitor C1 is not open circuited and the capacitor C2 is not short circuited. That frequency is called as a resonant frequency, and at this resonant frequency you observe the output is maximum. Whatever the input we are giving, 1/3 of the output we are getting at this resonant frequency. At this resonant frequency, the C1 is not open circuited and C2 is not short circuited. At this resonant frequency, you observe the phase shift between the input signal and the output signal. The phase shift between the input and output signal is 0. It is satisfying the Parkinson criteria for sustained oscillations. Parkinson says, if you want to get the sustained oscillations, then the phase shift between the input and output signal must be 360 degrees or 0 degrees. So here at the resonant frequency, the phase shift between the input and output signal is 0. But at low frequencies, there is the output phase shift with respect to input, it will be in the advanced phase. Means with respect to the input, output phase will be changing from 0 to 90 degrees plus. But when at the high frequencies, the output signal phase shift is in the delay stage. So if we are giving the signal, then the output will be in the range of 0 to minus degrees phases in the delay, phase delay. What is phase advance? This is the input. Then the output will be like this. Then we are saying phase advance. Phase advance will happen at the low frequencies. What is phase delay? If we are giving the input signal like this, then the output will be like this. Then we are saying the signal is having phase delay. But when we are saying both signals are in phase, then if we are giving the input like this, definitely output will be like this only. Then we are saying both signals are in phase. Both signals will be at phase only at one frequency, that is resonant frequency. So we have clearly understood this circuit works as an oscillator, but only at resonant frequency it will give the sustained oscillations. We do not expect this to be work with any oscillations. We are expecting a sustained oscillations. In order to get the sustained oscillations, we have to operate this circuit only at the resonant frequency. Remaining frequencies are not useful to us. So in order to operate this circuit only at the resonant frequency, we have to calculate what is the resonant frequency of this circuit. Then the resonant frequency, we will get the resonance of this circuit at Xc equal to R. When the capacitive reactance will be balanced by the resistance, then this circuit acts as a resonant with frequency. Then the circuit is working with the resonant frequency. So the Xc is equal to 1 by 2 pi Fc is equal to R. Therefore, F is equal to 1 by 2 pi Rc. When both R1 and R2 are equal and C1 and C2 are equal. If R1 and R2 and C1 and C2 are not equal, then the resonant frequency Fr can be obtained as 1 by 2 pi root over R1, R2 and C1, C2. Now we are reversing the problem. This time I want to design a Wein Bridge oscillator with 1 kHz. So the resonant frequency is 1000 Hz. Based on this 1000 Hz, we can design the R1 and R2 and C1 and C2 values. As we discussed already, these two arms are deciding the resonance frequency. If resonance frequency is given to us, if the Customer says, I want to generate a signal at the 2 kHz range. I want a Wein Bridge oscillator with 2 kHz frequency. Then the resonant frequency is 2 kHz. Based on that 2000 Hz, we can calculate the R1 and C1 and C2, R1 and R2 and C1 and C2 values. So the frequency of this circuit will be decided by these two arms, series and parallel RC circuits. Similarly, when we want to, the resonant frequency we got, and based on that we designed the R1, C1 and R2 and C2 values. But now, what about these R3 and R4 resistors? They are deciding the gain of our circuit. In order to maintain the sustained oscillations, the gain of this oscillator must be greater than or equal to 3 initially, and then, so because we know this is a non-inverting amplifier. In non-inverting amplifier, the gain is 1 plus RF by R1. In inverting amplifier, the gain is minus RF by R1. So here, 1 plus RF by R1 must be greater than or equal to 3. Therefore, RF must be greater than or equal to 2 R1. These two conditions, if you are satisfying, you are getting a very good signal with a very high gain at the resonance frequency. Wein Bridge oscillator we have already discussed. It is working in the audio range frequencies. That's why, because we are choosing it for the audio range frequencies, we are taking the RC circuit. These two arms in the Wheatstone bridge, they are concentrating on the resonant frequency. If we want to change the frequency, then we have to change the resistor and capacitor values in these two arms. But the output voltage amplitude will be decided by the R3 and R4. We already discussed this circuit is acting as an oscillator with the stable output only at the resonant frequency. We discussed about the low frequencies and high frequencies. At both these frequencies, there will be a phase shift. But only at the resonant frequency, the criteria of the Parkinson is being satisfied. Only at the resonance frequency, we are getting the 360 degrees or 0 degrees phase shift. Only at the resonant frequency, we are getting the maximum output. That's why we are neglecting the remaining frequencies. We are concentrating how to operate this circuit at the resonance frequency. Then we are saying, if you want to operate this circuit at the resonant frequency, only thing you have to concentrate are R1 and R2 and C1 and C2. That's all. If you take the proper values, then you can operate this circuit at the resonant frequency. But how to select these values? There is a formula. Fr is equal to 1 by 2 pi root over R1, R2 and C1, C2. Based on these values, the resonance frequency can be decided. Now you have designed this circuit at a particular resonant frequency. But the gain of this circuit will be decided by these two resistors, R3 and R4. This is how we can design a very good audio frequency oscillator in the range of the audio frequencies by using this Wein Bridge oscillator.